So let's take a closer look at the action potential. Again, this is something you're definitely going to need to know. This is something you're going to visit in the physiology and biology sections as well. So this is probably a review, but let's take a look. So we have something called a resting membrane potential. So this is when a neuron or a cell is just at rest. It's not really doing anything other than sitting there in the starting gate ready to go. And at this point, based on the concentration of ions inside and outside of the cell, we've established what we call a electrical gradient, an electrochemical gradient. And it's referred to as such because we have charge outside, we have charge inside, and we've separated the amount of charge on purpose by design so that we can make the inside more negative than the outside. So the inside is minus 70 millivolts in relation to the outside. And we accomplish this by differentiating the concentration of two specific ions, sodium and potassium. So sodium, we've all heard of, is salt. It's abbreviated Na+. It carries a positive charge with it. And then there's potassium, which it's abbreviated with a K, and that also has a positive charge. So what we've done is we act like I did this, but what evolution, nature, science has done is created this gradient with more sodium on the outside and more potassium on the inside. And we've created this electrical potential, which is at minus 70. So we say that the inside of the cell is more negative than the outside. So it seems like an odd way to say things, but that's how they decided to do it. So the inside is more negative than the outside. Now, how do we maintain this difference? That's done through a sodium-potassium pump, which requires energy, so it's an active process. Think of a sump pump or a bilge pump that's constantly taking something and spitting it out, but it's doing it at the expense of energy, and it uses ATP as energy. So we call this the sodium-potassium ATPase pump. And it does it in a relationship of 3 sodium out for 2 sodium in. And remember I told you there's a higher concentration of sodium on the outside, and there's a higher concentration of potassium on the inside. And so what happens is the basic laws of physics tell us that things want to go from an area of high concentration to low concentration, right? That's the definition of diffusion, basically. So there's a drive for that sodium, which is outside, because there's more of it outside, to wanting to go in. And so some of it does find its way in. There is a leakage current, and some ions do sneak their way in through. And so that trickling effect is that you end up getting some more sodiums coming in. But we want to maintain that minus 70. And so this pump allows us to maintain that by taking 3 sodiums out for 2 sodiums in. Now let's do some basic math. 3 minus 2 leaves us 1. So we're actually we're removing, because it's 3 out, so we're removing an extra sodium. So we're removing an extra positive charge out of the cell. If you do that over and over and over time, we keep moving out 1 positive charge, so 3 for 2, 3 for 2, 3 for 2, we continue to make the inside more negative. So this is one of the ways that we actually maintain and achieve that inside being more negative than the outside. Now, in the process of an action potential, once a stimulus is applied, then you're going to see opening of voltage-gated channels, which we'll take a look at in another figure. But basically, there's voltage-gated, so like the name implies, once there's a change in voltage, it's a gate. It's going to open the door. It's going to open the ion channel, allowing whatever ion that channel is designed to allow access to come in or out. So in this case, we're talking about a voltage-gated sodium channel. So the change in voltage will open it, and it will allow sodium in. All of a sudden, all that sodium that's been waiting outside is just waiting to get in. It's waiting to get into the party. The doors are open, and they're going to go rushing in, okay? Now, all the sodium ions go in, and they carry with it the positive charge, and that's why you see their charge going up. So as the charge goes up, that is the sodium going in. Eventually, all the sodium that's going to get in gets in, and that's the peak of the top of this action potential curve. At that point, the door closes, okay? So party's over, door closes, and now you start to see it falling because we, at the same time, are starting to now open voltage-gated potassium channels. So like the name implies, it's based on a change in voltage is what's activating it, and it's allowing potassium in. Now, that voltage changes because of all that sodium that just rushed in. So that change in voltage due to sodium caused an opening of the potassium channels, which are also voltage gated. Now, once the potassium doors open, they want to leave the inside of the cell because they have a higher concentration on the inside and they want to get out. Because remember what I said, the laws of diffusion say you want to go from an area of high concentration to low. So their drive is we want to get out of here. We want to go out. So the analogy I like to use is think of being in a crowded elevator and it's jammed in there and it says maximum capacity 12 people, but you somehow have squeezed out 15. And there's a couple large individuals that are extremely sweaty right now and you're jammed in. Do you really want to be in that elevator? No. Once those doors open, what happened? You get out of that elevator, okay? So use that analogy in your head. We got an elevator, a big sweaty elevator, and as soon as that door opens, that ion channel opens, everything is rushing out. So the potassium goes rushing out, and that causes the voltage to fall. And it does so quite efficiently. You can see it drop. It does it so well that it actually dips below minus 70. But then those voltage-gated ion channels close as well. And then we have this reestablishing of that resting membrane potential through the sodium-potassium pump and other mechanisms, and then we return to rest. So that whole process of rest, rise, fall, and return would be an action potential. Now, I just explained this whole thing in a couple of minutes, and it seems like a lot, and you're probably thinking, wow, this must take a couple of minutes to happen. Well, the answer is this actually happens on the order of milliseconds. Milliseconds. So you have to appreciate that. A lot is going on, and that is how a signal is actually passed along the length of a neuron. So if you think of things like, right now, I ask you to snap your fingers. For that to happen, I am sending a signal from my brain all the way down to my hand to snap. And that is through a process of several synapses. That is synaptic transmission happening live. You put your hand on a burning stove, and how quickly do you move your hand away from that burning stove? Extremely fast. So this is the science nerd in me getting extremely excited about this process because it is so fast. It's eloquent, and it's doing it through so many steps. Now, this process, we went into a decent amount of detail here, is going to keep coming up. And so when I say, as an action potential propagates down a neuron, I'm referring to this process. Now, more specifically, we're going to have to get into how it actually travels down the length of a neuron. So that action potential doesn't travel exactly like a wave, if you imagine an ocean, but it does so kind of. And we'll see what I'm talking about. So this wave of depolarization travels down the length of an axon, but it doesn't do it in a consistent fashion in your typical myelinated neuron. So this is mediated by those voltage-gated sodium channels that I talked about. The electrical potential crosses the plasma membrane quickly to restored to a resting state by the voltage-gated potassium channels that sort of off-switched. And the action potential travels down the process called saltatory conduction. That is a term you need to know. So that's what I mean by it's not traveling as a consistent wave. If you think of an ocean and a wave coming in, you have this nice wave that travels all the way down into the beach. Now, as an action potential, we actually have this hop, skip, and jump method in terms of the wave actually hops and jumps. That process of jumping is called saltatory conduction.